start from the beginning. All right, and you can just tell me when to go to the next chart.
Sure. Yeah. Hello, everyone. My name is Wang. Like Frank was talking about, I've been working with Frank for quite a while. And then we are in the spacecraft engineering branch from the engineering directorate from JSC. And so today we'll be talking about some of our work, some of our current work and previous work along the way to see the pathway that we have been taking for the last, I would say, 10 years or so. Okay, next chart, please. So our team basically supports this overall themes of human spaceflight explorations by including how do we include technologies to augment crew operations, right? This is on Earth, on orbit, lunar, so any opportunities that we see as that. And so we do have a laboratory, it's called the Advanced Operation Concepts Laboratory, that we created to create these infrastructures to allow us to explore some of these things here in this framework here. Next chart, please. So here are a kind of a laundry list of technologies that we've been tracking, and some of them that we're a lot more heavily working in, and some of them that we're definitely just tracking in and seeing what the industry and what these things are going here. Specifically from the visualization standpoint, there are the newest and greatest hardware. We definitely got all those things that we have tested and evaluated along the way. And as well as the rendering software, primarily we are both Unities and Unreal shops with these sort of 3D graphics type things, as well as the 2D type of display type of technology from a visualization, from a display and visualization standpoint. And from a sensory feedback standpoint or the actuation standpoint, we have been looking at, we have work on the various tactiles and haptic sensors to go along with the things that we are manipulating with, and also we've been working with the acoustic or the sound area. Of course, the hardware itself, which is kind of stabilized in terms of some of the acoustic or sound technology, but more importantly, there's huge advances in the software area. We've been working with Google's on their dialogue flow and speech dialogue systems and speech recognitions, as well as speech natural language processing type work. Including transcriptions, as well as automated transcriptions, as well as a speech understanding and conversations piece. So those are sort of a software area that has been continuously fostered throughout this, and then how we are actually incorporating some of these technologies into the overall themes that we're trying to do to facilitate crew operations, or in terms of space human operations. And in terms of rendering, we're looking at quite a bit on the cloud rendering using the various technologies that we've been looking at with the Azures, as well as the Azure platform, as well as the platform to do some of our storage and rendering type activities. And a while back, we have been looking into the sensor, the smell sensor technology, but we haven't been looking too much of that. Have not been too much progress of that. That's certainly something that we're continuously keeping track of. Back in several years back, that we have been looking at some of that. On the tracking technology area, there's definitely a lot of things are going around, and as well as in the early days, we're actually doing a lot of the sensory processing ourselves, some of those positioning sensory processing ourselves. Okay, and then in terms of IoT device, that we're looking at the various sensors to capture the environment and capture some of those activities that we're doing. In simulations area, that we are working both with discrete event simulation type, which is a state machine type simulations, and knowledge representation side to actually using the modeling techniques all the way from system engineering, SysML type modeling simulations to produce this, what we call it, a discrete event simulations, as well as our sister branch and interfacing with our sister branch in terms of building this sort of physics-based simulation. So integrating with those simulation technology is another area that we have been heavily working on as well. And recently, I think everyone are looking at the big machine learning type algorithms, and also the intelligent system, sort of conventional algorithms in terms of intelligent system, intelligent agents type things that we're looking at as well. So some of the deep machine learning type stuff that we're looking at, both prognostics as well as this sort of a cognitive, sensory, and in combination with the speech system, natural language understanding, as well as the automated speech recognition, so ASR type technology. So we've been looking at from both the mostly from the application standpoint of how do we actually utilize these applications, and developing this sort of a prognostic and diagnostic type routines as part of our back-end processing that's needed in order for these things to happen. And in terms of command and controls, i.e. that we're in this particular case that we're looking at the different I/O modalities that we're looking at, as well as integrating that into our applications in terms of gestures recognitions, using voice to do command and controls, looking at trackings to do sensory analysis, as well as the BCIs to actually doing some of those controls. So we can, along the way, we can see some of those technologies that we've been definitely looking at as well. Yeah, in terms of modeling development, we do some of that in terms of getting the model development and integrated into our model, but therefore also our sister branch are actually very much into developing the assets and developing a model that can be shared across the agency, across, at least in our human exploration, human operations perspective, and as well as design of the future spacecraft's perspective. Okay, and human health performance area that we're looking at all those sensors, those biometric sensors, as much more of a processing for those processing for the different groups of these sensory device, and where the kind of a data processing or the IT type of persons, information technology type of persons that we are looking at some of those things. So I can show from later chart we can show some of those examples that we've been looking at. But overall, our backgrounds, so we're really a computer scientist and then computer scientists and architectures to support this type of things. So we've been looking at quite a bit of the cloud computing, GPUs computing, as well as the sort of overall data management aspects about this. And that's finally, well, the newest things that is out there, I think the Claytronics type things that we've been just keeping track of what's going on with that. So that's actually the set of technology, quite a large set of technologies that we've been looking at. So really what we wanted to be able to do is actually how do we actually facilitate the type of problems that we're looking at. Frank, can you switch to the next chart, please? So the area of problem, the domain that we're looking at is how do we facilitate to make the operations more efficient, to get the crew more autonomous, to get the operators to be a lot more autonomous and providing the right information at the right place at the right time. Okay, so this includes in the real-time operational world, and we have looked at quite a bit of maintenance type application, and we do have a procedure execution system as one of the foundational pieces that we have in our backend to actually to make all these things happen. In the training domains, we're looking at quite a few things in the medical areas, in the maintenance area, and the procedure execution area. Those are we put it into the to put the operations. One is the real-time activities. Another one is the really how do we actually prepare the operators to perform their tasks. So one is prior to performing the task, and the other one from the real-time ops standpoint is how can we, they're at the heat of the battles, what kind of support that do we need to give them while they're actually doing their tasks. So that's how what the distinctions between the first bullets are. In terms of the analog environment applications that we have done is much more in terms of looking at designs and producing, evaluating designs in a VR sense, and as well as emulating some of the analog environments for scientific applications. So you can see a couple of those applications that we have done in that area as well. In collaboration of design area, that we've been looking at some of those ideas of people are evaluating their application, evaluating their designs collaboratively and things like that. Those are another area that we have been looking at in somewhat, but a little bit, not as much right now. But in the planning and scheduling area, that's the area that we have the background, certainly from the background of the intelligent system planning and scheduling application. That is another interesting area as part of the important as part of the ops tools that people are using. So that's another area that we have been looking at in terms of the planning and scheduling type problems. In human and health performance support, in those there are quite a few things. Countermeasures, how do we actually providing them the different tools that we can provide, or different software, or different trainings, or different different set of exercise type of things that we can provide for the users to get their visual to perform the countermeasure activities, to facilitate the performance of the countermeasure activities, as well as that we're taking psychophysical sensors to actually taking the state of the system, to capture the state of systems, not only in terms of their heart rate, these sort of physiological state, but also psychological state, as well as in terms of capturing their workload measurement and utilizing some of the biometric sensors to capture some of those, is another area that we are heavily working on right now. In the mental health area, a couple of years back, we have been working with the dementia training facilities, so developing training systems for training system for the caregivers for the dementia patients as well, for the people who is taking care of dementia patients, to actually providing some of their VR type of activities for that type of work. That's a couple of years back that we've been focusing on that as well. And eye health in terms of the ultrasound type things that we have been doing a couple of things on that. And of course, we're doing quite a few outreaches. So that's kind of the problems that we're looking at to facilitate this overall general area and how these things could fit together. Next chart, please. So the question here is, how do we map the technology needs into the problems that we're trying to solve? So a way that we're capturing that is through this AUI type of themes that we are looking at. AUI stands for Adaptive User Interface. The idea here is that we use the biometric sensors that we capture, and we produce an architecture that will actually collect and synchronize all these data, and going through machine learning process, and you'll be able to determine the cognitive state, their workload, their whether that they're channelized, the attention embedded into the different state of mind of this user, and then finally convert that into a adaptive display that this person needs. So this is truly the right information at the right place at the right time. The amount of information that this person can get it's really where we are. So that's the overall themes that we're able to encapsulate all these ideas into kind of a single thread of things that we're working on here. So the adaptive natures not only can be as simple as adapting to the device that you're holding on, right? I only have a cell phone type interface, and what kind of an interface do I give them given that? So it could be adapted to the environment. It could be adapted during their workload. It could be adapted during this. So the concept of adaptation can be quite encompassing and quite generic. But this is really the framework that allowing us to think about and categorize these set of problems that we're working on. Okay, so I'm going to stop just a little bit. That's kind of where we are as in overall themes that what we're going to talk about. And from then on, I'm going to kind of show you some of the examples that we have been working on, going on with that. Since that we're kind of running short of time, so I'm not going to ask questions. We can ask questions a little later. So here are some of the examples. Okay, next chart, please. Yeah. Here are some of the examples that we have done in the real-time operation support area. The first one that we have done here is a few years back, we actually done our own tracking algorithms to use a single webcam to be able to track any objects at any locations that we have. So this is the kind of, lead us into the post-estimation issues that we've been working on, and how does that applying to registrations for the augmented reality applications, as well as the general problem of estimating the human poses and things like that. So those are kind of the work that we're looking at. One of the earlier applications, the second one here is one of the earlier applications. What we did is actually develop a mission logistics inventory management system using both HoloLens as well as combinations with some barcode sensors, because for on-orbit operations. So do you mind to click on a video, a short video that kind of shows how we integrate some of these informations together in terms of the AR applications? Okay.
You want the mission logistics or the automated image recognition video?
Oh no, I want the second one. The first one, I think we can skip on that.
Okay.
So this applications that we have done is looking at what we call the cargo transfer operations. So the idea here is that there is a huge logistic issues for transfer vehicle. The idea here is for them to actually have to put the assets back to where it belongs. So everything is barcode. So we have integrated a barcode, linear barcode in there, as long as what are the equipments, and along the way I'll telling them exactly what directions that they need to put this thing here in as a applications. And we're actually including part of the planning issues in terms of developing planning issues for when and how do we actually unload this vehicle. So what you're seeing here is the real-time ops portions of that product, and that associated with the positions or where that they supposed to stuff to carry on and place the stuff, as well as the content of the stuff along the way as their hands-free operations. So those are sort of issues that we have done. This is one of the earlier applications that we have evaluated for crew on-orbit ops. Next chart. And you can go preview. Yeah, go take on the left. Oops.
Wrong charts. There we go.
Okay, good. The next chart, please.
Okay, there we go. This is the next one.
Okay, sure. Here's another application that we did for much more of a maintenance type applications. The first one that I can show you is kind of the training applications that we have done, that we actually incorporate a voice dialogue-based interactions to our procedure execution maintenance applications. You wanted to go into that? That's fairly self-explanatory.
All right, so what I'm going to do is I'm going to stop sharing and I'm going to reshare with audio on. So give me 1 second.
Okay.
Computer sound and
Grasshopper. What's my current instruction?
The objective of this procedure is to inspect all 4 corners for any signs of wear and looseness.
Grasshopper. Okay, got it.
Okay, good.
Make sure the 4 orange alignment guides have been removed.
You wanted to stop it a little bit?
Where are the 4 orange alignment guides?
Time. Well, yeah.
The orange alignment guides are located.
Pause a little bit. Sorry. Yeah. So the idea here is this is the a treadmill device on orbit stations. So there's a couple of technologies that I would like to kind of describe to you, hint it to you a little bit. So the idea here is this is a treadmill device that is on orbit, but every once in a while, or actually every month, they have what they call it the maintenance task to make sure all the bolts and all the all the bolts are still intact or it's tight, because this device is in motions, right? It's a treadmill that that folks are that actually the crew are exercising on, and the task here is for them to perform this maintenance task to ensure all the bolts and all the connections are all still good. And so from this training device, what we show here is what you're seeing here is one of the what they call it the snubber and cup area, that there are many of these interfaces that, depending on how you want to hold this, to actually check on the make sure the connections is good. So logistically saying, this is a fairly simple procedures, simple task and knowing what to do, but it turned out this thing here is about 10, 12 pages of worth of procedures, because the fact that not only the fact that they have pictures that they need to identify, and also words descriptions of how they wanted to check on the different interfaces. So a lot of them that we're actually providing a lot of animations, a lot of those activities to actually see, so can be assumed with the visual sense, right? So, and then on top of that, we have integrated a voice conversation agents on top of it, so folks can actually ask and be able to issue these commands in a very conversation-like type of natural voice-like type of interactions. So okay, so that's kind of the description. So we can let it play along a little bit, so you can
near each of the snubber cups.
Grasshopper. Okay, I've removed them.
Follow the R demonstration on each of the corners.
Grasshopper. Okay, I've removed the 4 orange alignment guides.
Which corner would you like to work on?
Grasshopper. Bottom right corner.
Inspect the connection points between the snubber cup and top arm. What type of wiggle did you experience?
Grasshopper. How do I test the wiggle?
The green hands are demonstrating how to test wiggle. Place one hand on the snubber cup and the other on the top arm. Wiggle the snubber to and away from you.
Grasshopper. What is expected wiggle?
Expected wiggle is minimal movement when wiggling the 2 connected pieces.
Grasshopper. Okay, I experienced expected wiggle.
Inspect the connection points between the bottom arm and K bracket. What type of wiggle did you experience?
So in this case here,
this is also expected
stop
wiggle.
just a second. So in this case here, we actually integrated a 3D printed snubber and cup, and then that in that case there is we are be able to, so the user actually can get a feel for exactly what they're going to have. But there are actually 4 corners of this sort of a snubber and cups type of instruments that is actually got onto this device here. As you can see that they're checking on specific interfaces. We tell them this is how you're supposed to hold it. And imagine that they actually have written as a primary means that they actually have written words to describe how to hold these and what mode or what interfaces that they needed to be checking on and all that stuff. Now all that can be shown in a very easy sense as a visual animation piece for them. And then notice on the voice side, there's quite a bit of repeat of using the wakeword engine. This is where we're still wanting to get rid of some to make sure the listener is listening. But since then, we actually have improved some of those interactions a little bit. But this is kind of where we are as part of the integrations of our procedure execution systems, as well as the AR systems on top of this. So this will be a voice, procedures, and AR and augmentation on top of this sort of a 3D printed type of applications that we put together as a demonstration system. But earlier, okay, that's it for this chart. Can we go back? I think you can just do it left, right? And still staying.
Yes. So can you see the?
Yeah.
We should be back to the chart.
I see it. Yeah. Now we're back in the chart. That sounds good. So the exact program that you're seeing here, we actually flew these things on board on US starting with STS-64, and now we're still continuously collecting data for how this user is using it. So this is kind of our on-orbit clip of the of exactly what the device is. So the crew members who's looking at one of the corner and that's the treadmill behind Soichi as part of this thing here. Can we show a quick video on that, please?
Yeah, and asterisk would be okay.
So as you can see, this is the treadmill device, and the in actuality, as you can see, it's really a quite difficult corners what we have. So from this experiment, we learned quite a bit in terms of actually the difference between what the on-orbit ops does and this sort of a training system that we're putting it for folks to use. So some of the issues we found was the corners that they have to work with is actually really at a corner area, and in fact the lighting situation is quite poor. So some of the image registration problem that we're going to have to deal with, and thank goodness the crew was pretty innovative and pop out their flashlight and will be able to get their recognitions that way after we actually providing some additional lightings to do the orientation on the registrations of those exactly places that we're talking about here. So those are interesting lessons learned, and how do we actually help them to do the registration, to image registration problems, as well as the alignment problems. So those are continuously things that we've been improving as part of this operation, as part of this operational things. And also, there's quite a bit of huge learning curve from folks start using this device. So there's that different things that we have learned as well in terms of getting used to on the device and how do we actually use it on board. But this is the beginning on what we have done, and a little bit of future on this version. What Koichi has was not a voice interaction systems yet, but that will be something that we'll definitely be considering adding as part of our tool suites for them. Okay, next chart, please. Right. Oh, okay. So the next one that you see is another application that we did along with our procedure system. Can you just go ahead and click the first one?
Now we need to go ahead and start the procedures. So we'll go
So,
with procedure number
can you stop it for just a little bit?
All right, that's identify the UI.
Okay, so the idea here is, in this case here, is we actually integrated our procedure systems with a live telemetries and integrating it with a UIA panel. UIA is an umbilical interface assembly. That's one of the panels that the EVA folks, extravehicular activities, there's procedures that basically as part of the preparations to going out for the for a extravehicular activity task, that they're preparing their suit as charging up their suit in terms of powers, in terms of gases, and in terms of fluids. So this is the procedures allowing them to do that. And from a technical sense here is we have basically integrated a telemetry value, a telemetries and command systems along with our procedure system. So we can watch that a little bit and then we can go on from there. So that is really where the difference is.
Okay, I hit the down button to go to the next one.
Turn on EMU
Okay, as you
power.
can see, it vectors the user and has a radical floating around exactly what switch I need to flip. Now, due to mirroring and what you're going to be seeing from a video standpoint, it's actually going to be slightly off, but that's again due to that mirroring piece. The actual user itself sees a floating green, flashing green circle and vectors the user as to which switch to flip and where to go. So I'm going to go ahead and flip on the EMU. Now I'm going to go over and look, and now automatically Pro-G takes me to the next step. Again, it vectors me to another floating radical to turn on the EMU power switch. Again, it takes me automatically to the next step. So it's forward leading the user in the procedure. Make sure EV1 1.2 power LEDs are green. It looks like they are. We're good to go. We go on to the next step. All right.
Okay,
This
so
is very
that's
important. We want
so
to make sure
that's
that we
kind
turn
of
on
where
oxygen.
we are in integrating this both
Oxygen to our
telemetry
astronaut
as
supply
part of
suit.
our procedure system. Next chart, please. Okay. The next few ones are very similar. So we have done it to another exercise device of using as another maintenance task. So I think we have seen some of those things, so we can skip on for those two, the next two videos associated with that. Okay, and another applications that we've been looking at is in the medical training applications or medical performance supports, as well as we definitely are looking at things from both the real-time operation sense, which how do we facilitate as part of the assistant, and also from a training sense as in part of trying to understand to help to the users to develop the muscle memory and as a training activities. So the first one, what we have done here is we integrated a magnetic GPS systems on top of the on top of our AR system. So that's additional sensors that were as a guidance sensors to do a carotid artery assessment using ultrasound. So can we show that quick clip on that? So the green arrow actually points to the where that placing the probe of the GPS. So we have a magnetic GPS on top of the wand. So we're registering against the wand, as well as the positioning where the positions of the user Yeah. Of course, this application, we got one of the big complaints from the user when we did the user evaluation is the animations are too big. Needing to get rid of some of the worksite activities, and a lot of them are, first time you know exactly what needs to be done. So a lot of those new area of research that we're working with the human factor people to actually improve our animation. We like animations, but a lot of the things that we learned from that here is it is just sometimes it's what can be too much and what what's the right amount of information that needs to be given to the user. All those things are all part of our learning process of developing a better assistant in terms of that. From a technology sense, we integrated the GPS sensors as well as, GPS sensor on top of this. So the next one is that we had a project that actually looking at further looking at this problem or looking at determining the ultrasound. There are two problems that we're solving in that. One is we wanted to be able to use the information coming back from the from the ultrasound images and determine what the positions, how do we orient the wand, right? So they can do a better scan. In this case here, we have to identify the kidneys in the first place. So the idea here is we actually trained a neural net to actually recognize to recognize where the kidneys is based on the ultrasound images back. So that's the first problem. How do we guide and develop a neural net system that allow us to know what to do and how to position the wand so a novice user will know what the target is, okay? And once that they recognize the target, you wanted to be able to actually give in this sort of a real-time guidance piece. Okay, the second piece of that here is we want to also train the neural nets to be able to recognize diseases. So those are two separate problems, but by using the machine learning type activities, machine learning type algorithms to actually facilitate the guiding process as well as the diagnosis process in terms of that. So can see a quick videos on that. If you wanted to click on that. Okay, so we actually, okay, in this case here, we can stop it just a second right there. So we kind of did the first activity. So we actually recognize what the images are. So the user currently have to hunt as what needs to be done. It has not done the actual guidance task yet, but is getting close to that area. We're doing the recognitions from the image to see what it is. So what we need to be able to train later on to our next iterations for that is to actually register the positions of the wand and to be able to actually recommend the directional arrows that you're seeing on the at the blue arrows that you're seeing, and as part of the guidance to saying go veer to the left, and then with the feedback that you will get from the sensor itself. So from a technology sense that we have integrated the imagery. We have integrated the imagery from the ultrasound machine, and then we're able to perform this sort of a real-time identifications of the objects themselves. So that's where we are on that. Next chart, please.
All right, there's a little bit of a lag when I switch charts, but let me do that.
Oh, okay. I will speed it up. So the next few charts is what we are doing as part of the performance measurement tools, as the part of the eye tracking tools that we have. And we're building that up to actually performing and to collect eye data in terms of how we're wanting to look at some of these. So I think those are pretty intuitive to touch. Why don't we show the YouTube real quick? So we do gaze tracking. Okay, maybe we want to scrub that a bit. So we can, so based on the information that was collected, so we'll be able to actually getting a kind of a heat map, a 3D heat map along the way. So we can be able to detect how long this thing here is, and maybe we want to scrub that a bit to the next things is called how much of the sensation. So you can begin to see how does user begin to looking at some of those things. So this is the fixation map, and as part of the data collection schemes that we're looking at. So this is mapped into our Vibe sensor, Vibe devices, and directional arrows. So you'll be able to see some of these basic informations that we'll be able to utilize and finally be able to incorporate it into our next systems. And as part of that, as part of that work, what we have done here is we have built up a data collection schemes to incorporate the numerous sensors as part of the task, including the simulator, and that data collection pipeline that we have built up, allowing us to collect the data so we can do a processing of that data and be able to start executing our sort of AUI visions of doing the cognitive state determinations, doing the workload determinations from that. So that's even we're using the we use the Air Force's task as our example showcase. But really, what the reusable piece that we have built up is that data processing infrastructure, and then we're hosting crowdsourcing operations to actually ask people to help us to analyze those data. So that's the data collection schemes that we have built up that can be shared and can be used for this type of activities. Next chart.
All right, so I'll talk the next few projects. Can everybody hear me? Okay.
Yep.
All right, so the first one is a system that we've been developing in collaboration with Buendo and several groups around the agency. It's called the XR Operation Support System. The objectives are to develop a system that allows multiple simultaneous users at different physical locations to don a VR headset and be able to support many activities. I've listed some of them here, such as real-time operations, planning, training, scientific visualization, collaborative engineering, human performance studies, PAO, and so on. So really the best way to see what the system does is to see a video that outlines some of the capabilities that we've developed so far. So Julian from Buendo put the video together for us. He was gracious enough to agree to narrate the video. So Julian, do you want to talk through what we're seeing here?
Yeah, so what we've built is a 400 square kilometer environment using Unreal Engine 5 and a combination of photogrammetry and imagery from the Mars Reconnaissance Orbiter high-rise imaging device to create this sort of multi-user environment where each individual user is tracked using motion capture. So they wear a VR headset, Vive Pro 2, and we track them in full body motion capture. And what you see there is basically several astronauts working on different equipment on the surface of Mars. We also have field camps and regions of interest that you can travel to, like lava tubes, and there you're also seeing active weather systems that can affect the performance of the astronaut when they're out on EVA. So visibility is diminished, and you see sort of the different weather systems such as dust devils and dust storms. We also have a MMSEV simulation where you're able to drive a pressurized rover to waypoints or locations of interest. The usage of a drone that is replicated to other users in the scene to be able to perform scouting or reconnaissance of areas prior to an EVA. And we integrated Langley Research Center's Mars habitat as well. And like I was saying, all of this runs using Unreal Engine 5. So we're able to sort of customize each EVA scenario using the software.
All right, thank you, Julian. We're a little bit over on time, so I'm going to just run through a couple of these other applications, just provide a very high-level overview. This next application is a project called Scientific Hybrid Reality Environment, or SHIRE for short. The objective of this activity is to develop a scientifically valid, operational, realistic hybrid reality analog environment that can be used to augment planning, training, and tool evaluation for geology type of activities. And given that we're over time, I'm going to go ahead and skip to the next one. Next project is a brain-computer interface project that we've been working on a low level for a few years. It's related to novel ways that people can interact with computers without the need for keyboards, mice, joysticks, or other physical devices. We've been investigating a couple of different approaches to this. One approach is just looking at the neurosynaptic patterns and mapping those to specific commands we want the computer to carry out. The other approach is to use visual evoked potentials, and I'm going to play just a couple of minutes or a couple of seconds of the video we put together here. I'll skip.
Just imported the brain.
So here we have Matthew Noyes. We're inside of a virtual ISS, and we're using visual evoked potentials
teleport down into the cupola
to send commands.
All right, so now hit the blue flip button. Now look at the start sickness capture button. It should be flashing blue. And that should start the arm animation, which it just did. So now turn to the right and hit the orange teleport to arm button. Watch this happening.
All right, so let me continue here. All right, another project we've been working on is a collaborative activity with JSC's Neuroscience Lab. So typically in VR systems, we do everything we can to keep a person from getting motion sickness. But on this project, we actually wanted someone to feel some level of motion sickness. The objective was to provide visual stimuli to simulate the vection effects that astronauts feel when they go from one gravity environment to a different one. And for these, I guess for all the projects, if you want to talk in more detail, please reach out to us. I'll turn it back over to Lei to briefly go over the last few activities. So, Lei.
Sure. So the next activity is what we call an intelligent personal coach. This is where we're start looking at machine learnings to actually characterize post-estimation type work. To actually we strapped on to a webcam plus a 3D webcam to actually determine the human pose and be able to actually offering corrective measure on how they supposed to do exercise in. So that's one of another applications as part of the countermeasure type tools that we're developing. Next chart, please. So that pretty much concludes all the application. We do quite a bit of outreach in terms of giving a lot of demos to many people. And another interesting application that we're looking at building is what we call the cupolar world applications that the crew can be wearing the HoloLenses to basically to determine what landmark that they're seeing above as one of the applications that we're trying to fly right now in terms of getting that work started. So this thing has a lot of applications for crew photography work. So essentially, crew currently are basing on a PC application to approximate what they need to do, and now we're actually can pinpointing to them exactly what information that they need to take on that. Okay, that's it for the range of work that we have been working on for the past few years, and many of them are active work. Okay, that's all.
All right.
Thank you.
So we ran